we are going to do a couple homework problems before we get back into it. So the main thing here, it says, oh, this is number 12 on 13.4, number 12. So it says equation of a circle. I know of curvature, we're going to figure the curvature part out. I'm not quite sure how we're going to go about that, but equation of a circle, this is what I want to look at. But really, because things are going to be moving and shifting, we might want to be cautious. And um, let me go a little bit further. So like I might have to shift it around a little bit, right? But there's something even further that I didn't really take into account. I said circle. What am I actually drawing here? What is that? It's an ellipse. So I was going way too much in that regard. So it probably is going to end up looking something like this. Okay, so that's what I'm thinking is going to be my answer. Okay, so I just need to kind of fill in the pieces. I need a radius, and I kind of need like where the center is. Now, I want to say that I'd like to just get it wrong and look at the answer. Do y'all ever do that? Come on, don't lie. Occasionally? Well then I'll go ahead and try it once or twice. And if I get it completely wrong, we'll start all over again. Um, and so I'm thinking this is going to be kind of like my answer. Now it says in terms of pi, that's freaking me out. Okay, so I don't know, but we'll see. So we have this curve, and it says use this instead, which is kind of nice. They kind of broke it down to something a little easier. I can now go back to the curvature formulas for that, which make it like pop, pop, pop. But what is it? What does the curve actually look like in the end? So 9t, and then we got sine of t. If my x is linearly proportional to time, it just keeps going forward. So in a way, like I'm just the more t, the more x. Very straightforward, basic stuff. So we should think of this kind of like just this guy. Like these are equivalent. So I shouldn't go crazy. I should just graph a sine function. So, right? The more x, the more time, and that's why the sine still works. Da 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 da. Like I'm not going in reverse. I'm not thinking anything weird. It just looks like this. So that's a good thing. It says at point 9 pi over 2 comma 1. So that's a little further, right? 9 pi over 2. How many revolutions is that? Four and a half. Well, okay, hold on. 9 over 2 is 4.5. Let's do a little bit of math. 9 over 2 is 4.5. So technically it's 2 revolutions because it's 2 pi every time. And so I would knock this guy out and say it ends up being a 0.5 essentially, right? A pi over 2. And comma 1 says it's at the top. So this was at regular pi over 2, like 1 pi over 2. And this guy here was at 5 pi over 2. And so then it's actually like right here at 9 pi over 2. That's where it really is. Go ahead. Yes. So it's got to be the top of it, right? But which top? Because again, didn't I say that we're going to shift it? So I got to be, a little cautious there. Good. So let's take this now. I'm gonna do a little bit less of that, more of this. I want to zoom in on that. So I'm gonna have to go like this, and then because we're really just focused on this part, the sine part here, and it's gonna come back and all that. But this is our main point of focus right there. Again at 9 pi over 2, and this is at 1. I did dashes because it's not, it's not really there. I've shifted it basically. So I need a curvature thing. I need a circle thing, right? So essentially, I'm trying to mimic the circle that would be up there. Now it might be this. I don't know. It might be this. I mean, I don't know. We don't know yet. We're gonna find out how big it is in a few seconds, but it's gonna look something like that. I can already tell you some things about it, right? Like the center will be either one of these guys. So when I'm filling in my formula thing, what for sure do I know about where it's centered? It's positive, yes. Which variable, like these are the three variables I have to find. Which, there you go. X naught is definitely 9 pi over 2 for sure. I don't know what the y value is yet. And I don't know the radius yet. But I can tell for sure that this guy is going to be at 9 pi over 2. Because it's going to just be however big or small, but at that location. Good? Okay, good. Some other neat tricks here is that it will go straight down. So in a way, like when I find a distance or something, I just know that's kind of where I'm centered for my y in a way, right? It's almost going to be automatic. But we'll see that in a second. We need to find curvature. Once I have the radius, I think all the rest will fall into place. So back to the formulas. Actually, I have my formula book here. Hold on. I'm like stuck in Cal 1 right now. Thank you. Let me erase some of this. Are y'all okay with the concept so far? Remember, I haven't even looked if that's the right format. I don't know what they're asking for, but I think this is it. Are y'all okay with the concept? Okay, so, because I could be totally wrong about what they're asking for. I'm not sure yet. So here we go. Curvature is absolute value of y double prime. And then I got the 1 plus y prime to the 2's 2 and then to the 3 halves. I'm just copying it down. So this is not too bad. I have sine of 5 over 9x. So then my y prime is you already did it for me. Thank you. And cosine turns into a perfect. Awesome. Now, I basically tossed that guy in there. And then we would get like a big formula for curvature at any x, yada, yada, yada. I don't think we need to go that far. I think that we can like summarize a little bit. Don't we know something for sure here about something? What do we know for sure about our x? 9 pi over 2? Yes, exactly. For sure, right? I don't care about the curvature at 0. I don't care about the curvature at 1. I don't care about the curvature at 2. I care about the curvature here. And that way I can literally just get my numbers, pop them in, and get a number, and I'm done, right? So that would be the only thing holding me. There you go. Something to take pride in. There you go. Disappointment like me. Yeah. Okay. Cool. I'm gonna do this, I think. There. So looking at the picture, like, are you good math-wise though? Okay, good. Okay. So looking at the picture, I'm gonna erase my other colors because we don't know what the radius is there. That was kind of just guessing stuff. Okay, it's harder than I thought. Okay, that'll be good. Okay, okay. No. Good. Okay, okay. 9 pi over 2, whatever. So this is at 1, and I need to go down a radius of 81 over 25. But what is that number, right? Isn't that like 3 point something? Blah, blah, blah. Right? Because like 75 would be 3, but it's not 4, so it's 3 point something. So I know my picture doesn't look very good, but my radius, this is 1. This is where I'm getting nervous because I don't know. This is 2. This is 3, and that's supposed to be the radius? That's the radius. Right, right. Like, whoa. Now, I know that I didn't draw my sign very well. Whatever. So I'm just gonna roll with what I got. Hopefully this works. So yeah, it's really, really far down there. So I need to find now what my y naught would be. How would I go about finding this y value down there? There it is. I have 1 is where I start, and I say minus my radius. Exactly right. And I don't want to go too specific because I don't want to. I don't know. You don't have to simplify, right? I'm going to say that value is 1 minus my radius, and then I'm going to say it's my radius squared. Okay. I have a weird feeling that that I had to like square root this ahead of time. I'm getting nervous, very, very nervous. But that's my whole answer right there. Okay, that's my whole answer. Oh, really? Oh, okay. I mean, if you. Okay, okay. I'm gonna expand this a bit here. Just do this there. Okay. And I'm gonna be a little silly. I want to see if it'll accept me being a little silly. Oh, no, 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 no. Wrong place for a square. There we go. Wow. Okay. That's good. Yeah. Yeah. Even the unsimplified version. Okay. I'm feeling a little bit better about my math lab where I could do that, you know. That's a good thing going forward because we definitely will have some fractions and weird things like that. Yeah? Not too bad in the end. Any questions generally, specifically? Can I look at 13 and see similar, right? Yes. Let's look at it. So, actually, it is similar, but it actually is a whole different problem. Did I do this one? It looks so classic. Let's do it. Are y'all okay doing this one? Yeah? Yeah. This is a classic right here. This is one that like even WebAssign had. So like I've done this problem many times. So an ln function, you know, natural log, it's going to look like this. And there's a point where the curvature is maximized. And this is nice, and I want to use this, but just on the side, like what is it? How is it maximized? What does it look like? Well, if you zoom out, okay, then it looks kind of like this, and then it does this. I mean, that's kind of like what a logarithm looks like. Notice that it's not really flat, but it's flattening, right? And then here it almost is flat. I mean, that's an asymptote there. So somewhere in the curve is where we're going to have like a bigger, no, I mean a smaller maximum curvature, smallest radius. There you go. The smaller radius will be right here, something like this. Why not somewhere else? So like over here, to basically like replicate this flat thing, you would actually have to have a circle that's like really, really big to kind of like make this neighborhood similar, and that's not good. So that's a really big one. Same with down here. To kind of replicate that curve, it would almost have to be like a flat line, which makes it a huge, huge circle. We don't want any of that. Minimize my circle to maximize how much curve it's got, right? Because if it has little curve, it's like just a straight line. So we don't want straight lines. We want a lot of curve. So that's what they're asking for, and that's why this is a classic problem. They're wanting somewhere in the middle there, right? Actually, just erase all of it because we're going to have our other picture. This guy, right? So I'm assuming that it's going to be somewhere around right here, okay? And it could be like right here on the axis. It could be a little bit above. I don't really know. I can't remember the technique at that point, but that's fine because we're here to learn it, right? The same thing though, because we have a y equals, we can just do the same formula as last time. So then y prime, what would I get? But then, yes, times 3, which ultimately makes it just 2 over x. Kind of interesting how that works. Very good, though. And then y double prime. Here, let me rewrite this. This is x to the negative 1. Yep. So the negative 1 comes down, so negative 2, and then a negative 2x, because you subtract it. Very good. Yep. Or you could say 2 over x squared, like you had said. Much cleaner. Very good. So we have these values. Now I can just plug them into the formula and all that. Negative. Thank you. You know me, I'm going to mess it up. So that was good. Thank you. Always keep me on track there. So absolute value double prime 1 plus y prime squared to the 3 halves. So absolute value of this dude. And then I've got just 2 over the x squared. That doesn't look good. 3 halves. To make it like easy looking, I'm wanting to get like a fraction over a fraction. When I square this, I don't want to. This is good. This is good. It's good. Common denominator. This is just the basic algebra stuff. Are y'all okay with? I would dive for it, but then all these chords would get in the way. This x squared could come out as a regular x with the square root part, but then it's still cubed, right? So technically it turns into like an x cubed in the bottom. Let me make sure I'm doing this right. It looks kind of like this. It's okay. It's okay. This is just calculus 3, right? Take this. I'm going to flip it up here, and they cancel a lot of x's. So I think I get 2x over this stuff here in the end. Whew, and this is my curvature. And now we're going to like do stuff with it. Is that okay? Good with the process? Good with the process? You ready? Okay, cool. So I take this, and then I need to find the maximum curvature, right? So that's going to be like k prime equal to 0. And I don't think we can have a minimum curvature because that wouldn't make sense, right? Not for ln function. We just wouldn't get it. So whatever we get will be that maximum curvature we're looking for. So I need to take the derivative of that thing. I'm feeling quotient rule. What are y'all thinking? You're like, no. Yeah, I know. Low d high minus high d low. Oh, don't have a lot of room there. Chad, are you sure about this? No, no. Okay, here we go. Okay, let me start over. Low d high minus high d low, and then don't try to correct it. Just erase. You know what I mean? It's a 1/2 now, and then that's a 2x. All divided by the square of what's below makes that into a simple cube. Just a simple cube. Wow. So then you go to Desmos. Honestly, yeah, you could at this point, but I'm gonna try. I'm gonna try because it's a classic problem. Combine like terms. Oh, and this 2 right here. So like these guys cancel. So I get a 6x squared. And this guy's got a 2 in the front. What I'm going to also do is a little bit weird. I'm going to split this guy up into a whole and a half. This guy will only have a half. And then I have my cube in the bottom. Okay, pause. Did y'all see that little move that I did? Halves. So that's like 1 plus a half. So I said 1 plus a half. But that way I can start to like I can actually pull them out and then mush it with this one. So that's going to be 3 minus a half. So that's like 2.5, isn't it? Negative 2.5. So then would this then be 5 halves down here? Because 3 would be 6 halves. I'm getting rid of one of those halves. Like it's canceling it away. If I'm making a mistake, tell me. Oh, gosh, there I go again. 5 halves. But none of that denominator will matter in a second because we're solving for x, which means in the top equals 0. Like all this doesn't even matter. We're just really going to look at this guy in a minute. So I got negative 4x squared plus 8, blah, blah, blah. That thing equals 0. So I take this guy and I'm going to solve it. I can factor out a 4. So then I got negative x squared plus 2 is equal to 0. Move it over, square root both sides. We get imaginaries. I'm joking. No. Square root 2, and it's positive knowing the situation that we have. That's what I'm thinking. If I have square root 2, it's not asking for the equation of the circle. It just says, what's the curvature, right? So then I could just say, like, right here, like, what's the answer, essentially? Plugging in square root 2, so I got 2 plus 4 is a 6. And this guy would just be, so 2 square root of 2 over 6 to the 3 halves. I know that looks kind of weird, but let me do this and see if it works. And I can go back and explain whatever if it does or doesn't. We don't need to simplify in this class. Wow. When I get it right, wow, that's nuts. So I want to minus this guy out one. Good, 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 good. It's a lot of work, but maybe there's like a trick. Is it always square root 2? Or is it a 2 because there's a 2 in the front right there, maybe? But then square root 1? I don't know. Or maybe I will. Yeah. Similar question. So I'm thinking square root 8? I'm guessing it's going to be still something like that. I don't know what this answer is going to be. I know. I was just... It says both my answers. Well, then maybe there is... Maybe there's a pattern I'm not seeing, but, you know, I shouldn't see the P word, especially when I'm being recorded. That means we all got to do it, okay? Anyways. Good? Any other homework questions? I'm always here for homework questions. Oh, yay. Okay. Good? All right. Good. Let's keep cruising then. Yay, back to this stuff. Oh no, not the triple integral. Yeah, not there yet. Yeah, I know. It all went out the window. Oh, we're getting there then. Okay, so we had the limit stuff. Yeah, that was not... So what you had missed was on my video. Moving on. No. Wow, Chad. No. Just partial derivatives. So this is del, and it's just the same as d. I mean, del f del x df dx. So del stands for d. Oh, well then we're good then. Oh, we... This is what you missed. Perfect. And this is what you don't need. So that's perfect. If you know what we just did with the dels and stuff, you're good. This is a formula that we're going to use, and there you go. Like, really, there's nothing new there. Okay, good. Sorry, you're right. Thank you. I'm off on my days. We did this one, right? I know we did. U's and V's for the new one? This is the one we need to do? Should I just have this as like a you do to start off? No? That's okay. I'm fine with doing it. I love doing the math. So notice that it says dz du, del z del u. So we need to do both of them. And we need to basically start with our z. So this is our function that we're going to kind of work with here. I have an idea. Should I go down the bad road? Plugging in only one other letter is x. Yeah? That's it. So the way that I was saying not to do, if at all possible, is to not plug it in immediately, but to do all the little chain rule things. But this one, it almost seems like it's crying out saying, plug me in. And then I just do it normal, right? So I want to see if that works. I know that it's going to look a tiny bit complicated, but it's going to be very straightforward now. So I'm looking for just literally the partial derivative in terms of u and in terms of v individually. So z sub u, what's the derivative of arctan? Isn't that 1 over something? It would be like u prime, that would be over 1 plus u squared. Okay, cool. So let me do that part, not the prime part. We'll do the prime in a few minutes. So 1 over 1 plus, and then my inside unchanged, right? Squared. And then I take the derivative of that inside. Now in terms of u, I get what from this guy? And the derivative in terms of u here? In terms of u. Oh. I know the Latin u's and v's are all mixed up. I get it, but well, I forgot we're doing perspective. Correct. Only u. Exactly. But then we're going to do that cosine thing for the v here in just a second. I have one question. Go ahead. Thank you. You know I have to get something wrong. Okay, thank you for that. I'm just making it look pretty. And because it's squared, there's nothing really we can do here. Notice that, here we go. Notice that we're just going to have to plug in the numbers, and we're done, all right? Because that's all they're asking for. We'll do that here in a second. Let's do the z sub v. 10 in the top. And now when I take my derivative this time, I get, from up here, 0. There you go. Clean it up a little bit. And I think we're ready. So in the end, that was not too bad. Remember, we tried that one other time on the previous problem, and it did not work out very well. But here, it's working out much, much better. So, yeah, let's plug it in. So if I got ln3 for my u's, then the ln and the e, a 3. Yeah. So I basically get a 3 right there. And then a 3. And then v is pi. Sine at pi is sweet. So that's 9 plus 1 is 10. That was nice. The only thing that's changing on this is the numerator number. So what is cosine at pi is? There we go. Let me flash the answers. We're even close to that. Okay, hold on. Give me a second. Hold on. No, that's all what we were going to do. There we go. Yay, we did it. And it looked pretty. So the thing that you missed, because this is not what we did yesterday, what you missed was the chain rule, actual chain rule. See, if I were to plug all this stuff in right here, I would just get a whole total mess, right? So doing our derivative that way is not very fun. But if I take my derivative of this guy individually, it's not too bad. And then individually start plugging it back in afterwards. Yes. Yeah. Do you remember implicit differentiation from Calculus 1? That's what it is. Yeah, like another name for chain rule is implicit. And so, I'm not going to ask who you have because we're being recorded, but did they do the derivative of x is a 1, derivative of y is dy dx? Yeah, that's the classic way. We did that once. We also did like the little primes. So like derivative of x is x prime, derivative of y is y prime. You just kind of like toss it all in. Well, yeah, my video says it all. No. Yeah. Well, what's the derivative of a number? That's why we can't do that. Right, because we would get 0 every time, and I can't do it. That doesn't work. Cool. Yeah, but there is like a key strategy is when can I start plugging it in, right? Yes. Totally understand. Of course. Man, I'm totally fine hanging out. No problems at all. Y'all are a good crew. I got to say that. Thank you. Yeah, it's fun. Huh? Not bad necessarily. Like that would be behavioral in my opinion. But like maybe like a tough crowd would not respond. Some folks that just don't like reply at all. I don't know. Yeah, but y'all are good. Yeah. Plus, if you were bad, I probably wouldn't say it. So you know. Oh, are you good? I just started moving. I can wait. He's in the zone. Are you? Am I okay to scroll? Yeah, I can wait, bro. I'm totally fine. I never want to rush. Never. I have a tendency to just. That was so fun. Let's keep going. And it's just like, whoa, Chad, whoa. Totally okay with that. So 14.5, directional derivatives. It's not hard at all, except that it's a formula. So we were talking how this was del, and this is also del. It's just lowercase, uppercase, right? As related to this is delta versus, there we go, delta. But it still means the same thing. It means derivative. D means derivative, right? So we're looking for the derivative. The gradient is super cool because it's just your derivatives in those terms, in those components. And so like this is way too fancy. That's way too fancy. It's actually just this. Partial derivatives in terms of x, y, and z in the x, y, and z locations. That's it. Very, very easy. And we're going to keep using this as we go. But note one interesting factoid. We have an f of x, not a vector. We're going to a gradient, is a vector. So we're going from a scalar to a vector, right? Just like a dot product goes from a vector to a scalar. So it's kind of like we're going reverse there. So it's very simple. Take some derivatives, walk away. Now, the directional derivative formula has it multiplied by u as your unit vector, but it specifies this is a unit vector, but then we use u, that's not always a unit vector, and then you get confused. So I would like to add to your formula, divide by magnitude of u. Okay, that's like totally more official, okay? That would make sure that 100% of the time it actually does work. You have to divide by the magnitude of u. Every single time it'll be fine now, okay? So that's one little caveat. And they have that same formula right here. Again, they say unit vector, which, yes, but sometimes they're going to throw something else at you, so it's just weird. You can use the cosine to make it unit. Notice that right here is my magnitude, and then I have cosine. What's the range of cosine? -1 to 1, which makes you have unit, right? So that's a good thing. I've never used this one in my life, literally. I mean, if it pops up, cool. If it doesn't, whatever. I don't really worry about it too much, okay? So that's fun. Scroll a little bit. Okay, yeah. And this right here, again, these are really great formulas, which we will be using as we keep going. So tangent line to a level curve, blah, blah, blah. This is way too much. It's way too much. Let me simplify it down. to this. Okay, I like that. I like that. You know, if you do you like theory? I'm going to do a little bit of theory. Are you okay with that for a second? Let's do some math theory. Kind of like lets us slow down a bit. I'm gonna move this whole thing over to the other side. Just you don't have to do what I'm doing. I'm just being funny for a second because you know me. I gotta be silly. You know what else I want to do? I want to divide by this FY business. Just who knows? Yep, yep. None of this is required. None of this is required. I just think it's funny. You know where I've seen this before? That's the formula from last time where it turns into dy dx. Guys, you totally remember that derivative is slope. I wrote that last one wrong, sorry. What I just did was recreate the line equation. And that's what it is. It's a line. It's a line. You don't have to have any of that. Algebra. Now we're just kind of making it into calculus funness, right? Pretty cool, right? Silly me, remembering all these silly little formulas. But it's all interrelated, and that's why you had to learn this back in algebra, chapter 2, section 3, questions, 5 through 12. You had to do this. I'm going to move on from the theory. You don't need that stuff anymore. Yeah, I don't know. We might hit that one up. It's the same kind of style. See, you can see gradient, and that's, blah, blah, blah. I don't really care. So here we go. Let's find some gradients. I want to just find some derivatives. You're going to help me. We're all just taking partial derivatives here. What's the derivative in terms of x? Ooh, there is someone down there. So derivative ln. Satisfied? Is that a yes? So that was fx. F sub y. What's my derivative in terms of y? That's it? Too easy. Chad, you get the easy questions. Then I go to the homework, huh? F sub z. Not just that. There you go, minus 4z, and then yes plus ln of x. Very good. There you go. There's my vector. I went from a scalar function, because it results in a single number. Oh, yes. Oh, the z right there. See at the 2, it's going to come down?
Oh, I didn't even see that z.
I know.
I only saw the one z and the rest is non-existent.
Yes, yes. You got it. So we're going from a scalar to a vector. So let's do some of this, I guess. I'm going to plug it in. So this would be grad f at p. I'm going to label that one p. And it's still a vector. When I plug in 1, 4, 3 right here, I guess that would be 3 times 1 squared. 3 over 1. 2 times... What do I plug in here? 4. Very good. 4 times 3. And ln of 1. You got it. You got it. You got it. Cool. ln of 1, what does that make? 0. 6, 8, negative 12. There you go. Awesome. I'm going to go flash the answers right quick. Sorry. I'll be right back. There we go. Yep, we're good. What are we finding here? First off, what's a derivative? Slope. We're finding slopes. And if you look at these, again, think of it like this. Remember that little line equation funniness I did earlier? But they only had x and y. Now I have a z in there. And so if I have x, y, and z, if this was a line, this makes a plane. It's a plane, exactly. So what we have now are the slopes of our plane. Let me insert here tangent plane, right? Because derivative, tangent, same kind of thing there, right? Slopes of the tangent plane. And so just as like a rough example, I have some kind of sphere going on and I pick a point. There's a plane that is touching that sphere only once at that one point right there. Yeah, in all the directions, exactly, which create the plane. Perfect. Perfect. Yes. Pretty cool, huh? We could take these and start creating that plane immediately. Because look at what it is. It's 6x plus 8y minus 12z equals, and we'll figure out whatever the height is or whatever. But that's not a big deal. We find out later. There it is. Boom, done. Right? So yeah, there's very much usefulness to this going forward. This is like a baseline of what we're going to do like math-wise later. But yeah, that's going to be for another day. Definitely not going to do all that right now. We're just saying, hey, can you make this thing happen? Cool? Okay, awesome, awesome. Eerie. So this is the perfect example of annoying. Where they said, oh, well, you should be able to figure this out, unit vectors. And that's why I gave you that extra formula, I guess you can say. So directional derivative in terms of f is equal to grad f at p dot u over magnitude of u. That's the more, okay, it looks gross. Let me start over again. That's the more filled out formula. So grad f at p dot u over magnitude of u. That's the filled out formula. I don't think they did that up there. But again, that's at p, at point p is what that means. Or win, that's the win bar, like W-H-E-N, win. So yeah. What we need is some numbers. And we need some more numbers. And then we do a dot product. Right? This is a vector, of course. That's another vector. But there are going to be some numbers, some more numbers. You dot them, and you're good. Okay? That's the end. That's the goal here. So let's find grad f. And that's an easy one. What would be the derivative in terms of x? Oh, I don't care about that yet. Yeah, just f, grad f. Good. Comma, right? Because there's nothing else. Just y. Oh, I know. Perfect. I'm going to change my colors, I think. But yes, that's all very good. So I found grad f. But we don't want just grad f. That's going to give us way too many variables. And, like, I don't like that. So I'd rather immediately do grad f at p. Still a vector, but now we're plugging it in, right? What numbers would I get? 7. Yes, you're right. I'm sorry. I was looking at the A for, it's all flipped. Yes, 7. Very good. And the next one? Cool. I'll take it. -6. Are y'all okay taking some derivatives and then plugging it in? Right? The math isn't that bad. Right? The math is easy. Sometimes it's like, what are you asking for? Because they got the derivative. It's just, yeah, directional derivative. That's what they're asking for. So this is 1/2 of my directional derivative. That's this half right here. And I'm going to say dot, and then I'm going to have something else over here, right? Another vector of some kind. So then notice I don't have a u. So what's the only other thing I got? The a. And notice that a is not a unit vector. Classic. And that's why I stress very often we have to divide by the magnitude of u regardless. So yeah, let's start working on that. My a vector is 7, 8. Magnitude of a, which I don't even want to call it a. I just want to call it u because that's what we normally use. Oops. Magnitude, sorry. Yep. Square root of the squares. Yep. 49 plus 64. What is it? For reals? Okay. Math mastermind. I can't do that. And so I want to divide both of those by that. Just like that. Cool. We could take that square root and kind of like factor it out. That would definitely make it easier, but either way. All right. Well, now we just dot them. What's 7 times 7? Bam! So 49 divided by that square root plus, what's -6 times 8? -48. Very good. Same denominator. Hey, look, I got a common denominator. And just so that I'm like super annoying with you guys, I'm so sorry. There you go. Chad, you're annoying me so bad right now. Real quick, I'm going to flash the answers real quick. Hold on. Yeah. Yep. See, they're annoying too. Cool. So, what do we learn from all this? First off, it's not hard math, right? It's not hard math. Sometimes it's weird about what they're asking about. But once you get, oh, that's what you're saying to say. Did they say directional derivative? Did they say directional derivative? They said direction of a derivative, but I mean, you know what I mean? So sometimes we got to like, what are you asking for? And that's definitely going to be going forward, a lot of that. Any questions on the math? We're almost done here. I want to just look ahead. Same thing. I'd almost want to say just that's a you do. It is a you do, but do we have time? Let's try. I'm gonna let y'all try, and maybe if we don't finish it, we'll just do it on the brain. I know it looks so much more complicated, Chad. At least the point's at 0, 0, 0. Makes things way easy. Yes. Yeah. Mm-hmm. Would it? But when you're doing it in terms of x, let's say, the only thing that's x is right here. This is just a number. Sure.
That would still be the negative 3 e to the x would still be there, right?
Yeah, because it's just a number then. Yeah. So like, what's the derivative? Cosine goes to sine, right? Negative sine or whatever. And my y has a number in the front, or my z has a number in the front. That's it.
Okay. I just want to hold on. Am I reading too much into this, or am I pretty sure?
It's almost too simple, right? It's almost too simple. It looks complicated. Oh my gosh, no, it's way, way, way simplified. Yes. I also think it's kind of funny to analyze how y'all go about your business. We have some talkers that whisper.
I feel called out, Chad.
Got some folks that are silent. Some people that just keep staring at it, saying, "Am I actually right?" Like, what else am I going to do up here, you know? Other than stare at you guys. For time's sake, I'm just going to kind of do a little bit here. For x, what's the derivative in terms of x? Yeah. Yeah. You could have just said the same, but yeah, cool. No, I'm playing with you. You're right. It doesn't change, does it? There's no change at all because everything else is like a number. It just kind of hangs out, right? But now for y. And very good to say that we got negative cosines going to a positive sign. Yes. And then times z. I like that. Very similar for the next one. Very good. Very good. So now we just have a y. Got a little bit of room. Oop. I don't like that. I want it bigger. We got time. It's fine. A strategy, just because, there's so much to write and it happens. You could go downwards. We don't always have to go horizontal. You can go vertical. If that's still okay with you. Something kind of like this. At minimum, it definitely organizes things. Cool. When I plug in a 0, 0, 0, what do I get? Really?
Because the signs all go to 0, so anything multiplied would be 0. But the only thing that gets something is cosine.
Oh, so this one here retains a 1. And so then whenever I do that, that's a 1. So negative 3. And then this guy's a 0, and that's a 0, so the whole thing just goes to 0. Oh. Wow. Okay, cool. My magnitude of a square root of the squares. And it'd be easier if I just toss that into the front, So let's do this real quick. I got this silliness dot the 243, and then I'm just going to divide the whole thing by square root 29. So the only things that even matter right there. Right? Flash the answer. Yeah, that's good. There it is. Wow, that was way easy at the end. So the main hiccup was, of course, how does it look like to take a derivative? And it was almost too easy, Anyway. anyways. I'm gonna stop the recording.